Of course, when you have the PDF, you can compute the CDF by integrating it. But in this case, this integral, okay, when you integrate it, it does not have a closed form solution. So we cannot express the CDF of the Gaussian distribution in an analytical way. So we just define it to be some function, phi x. Okay, by definition, this is the CDF of the Gaussian, standard Gaussian random variable. We do not have a closed form expression for this. In the old days, we had some tables for this, but now, of course, computers can numerically compute this. And the complementary CDF, again, this has a special name. We call this the Q function. Now, you see, if you have an x here in this plot, you see this here is called the tail probability. Okay, as you see, it is the complementary CDF. This area here is equal to Q of x, this function here. Now, due to the shape of this distribution, this has some nice properties. Essentially, we have Q of minus x. Let's say this is minus x here, okay? Q of minus x, which is, well, let me use another color. Let's use green. Q of minus x is this region here, right? So you should see that Q of minus x is equal to phi of x, because let me show phi of x again, in yet another color. Let's say this is phi of x, probability that random variable is less than or equal to x. Due to the symmetry of this distribution, this is equal to phi of x. Okay, so we have this Q of x plus Q of minus x equal to 1. And obviously at 0, you have Q of 0 equal to 1/2, obviously, which is also equal to phi of 0. Right. Now, there is this error function. This has to do with Gauss's original formulation. You see, you do not have e to the power minus x squared over 2. You have something like e to the power minus x squared directly. So Gauss himself actually defined the standard Gaussian in a different way, which does not have a variance of 1, but a variance of 1 over 2. And the normalization coefficient is also different due to that. This function is called the error function, which alludes to the fact that Gauss actually derived this for astronomical error values. Okay, and here we have the relationship between the error function and the CDF of the standard Gaussian. If you need it, you can use this, but in this course, we are not going to use the error function. However, it is implemented in most computational packages like MATLAB. You have a number of error functions in certain situations. It's directly implemented, and you can use that relationship to actually compute the Gaussian CDF if you like. And in some contexts, the usage of error function is much more pronounced rather than Q or phi functions. But in this course, we will mostly stick to using phi and Q functions in general.